How's it going, AS Math? It's Mr. Knight here, and we are going to continue with differentiation. We were getting pretty good at using the power rule to find the derivative of certain functions. We know that the derivative now is just the slope of a tangent line for a particular curve. And now we're going to extend this idea, and we're going to just find the gradient of that tangent line at a specific point now. And we are going to use it to answer this question today. What's the change in gravitational force a 200 kilogram goose would experience walking at sea level? And then we're going to compare that to if this goose was walking on Mount Everest. What goose is 200 kilograms, you may ask? That goose right there. That scary looking horrible thing that Camber drew on the board. I'm going to use as inspiration for today's lesson, and so we are going to use Newton's laws of gravity. We are going to take the derivative of it, and then we are going to apply what we learned today in order to answer this question. So a little context to this, okay? Fg equals gmm over r squared. That is Newton's law of gravity between two objects. So the two objects we are going to look at later, the two masses, which are these m's, big mass is going to be the Earth, little mass is going to be the 200 kilogram goose, which is not that little for a goose. G is a universal gravitational constant, which I will provide, and then r squared is the actual distance between the goose and the center of the Earth. So I drew my little goose at sea level, it's going bonk, and then over here on Mount Everest, it's a little bit bigger, bonk bonk. Okay, so we're going to look at two different distances and compare them later on. Graphically, this is what it would look like. I told you guys that gravitational force kind of does something weird like this. And again, it makes sense. As two objects start to move further and further away, their gravitational force will decrease. But we want to know how much of a change it's decreasing by as it moves. So we will do that in a little bit, but we're going to put it on the back burner for right now. To do this today, we've already done part one for our 2 steps for solving these types of problems. The first thing is just differentiate our function like we have been with the power rule. And then we want to find what the slope of the tangent line is at a certain point. So if we're looking at a certain point, we're going to actually plug that x value in to our derivative function, and that will spit out the gradient of our tangent line. And you'll see that in a little bit, okay? So more of a traditional example is something that you'll see like this. Given that y equals this stuff right here, we're going to do 2 things. We're going to find dy dx, which is our derivative, and this is an alternative way to write a derivative with respect to x, because that's what we're using as our input. And part 2 is saying we want to find the gradient of the curve at point 4, 1.5, right? First things first, we need the derivative. And right now, using power rule would be a nightmare. So I changed it up like this. X to the 1/2 minus 8x to the negative 2. And now we can apply our power rule. And this is what we do. Do dy dx. Remember, we take our exponent. It moves out in front. And multiplies if we need to. And then we have to decrease our exponent by 1. Okay, and that's what we do for both these cases. And I just went ahead and simplified it even further and made it look a little different. Cool, we have the derivative. So now this is where that point 4, 1.5 comes in. So we don't need to actually use the y coordinate at all. We will actually find the y coordinate later on, but for right now, if you're given something like this, we just want the gradient. So that's what a derivative really is. You know, it is the rate of change for this function right here, and it's just represented by this function right here now. So we're going to just plug in 4 for x, and basically we're going to do a little bit of algebra, a little bit of arithmetic, and we're going to find that the slope of the tangent line at point 4, 1.5 is actually just 1/2 when we plug 4 in for x right here, okay? And it simplifies out. I decided to put this in Desmos so you can get a really good idea of what this is going to look like. We're going to hide this for right now. We'll put this back up, We'll zoom on in. Okay. So this is the point that we are looking for, and we wanted the slope of the tangent line, so it should look something like this, what my mouse cursor is attempting to do. And in fact, if I go ahead and I put a, just like an equation of a line that has a slope of 1/2, oops, 1/2 x, you can kind of see, and if maybe I play around with this a little bit more, yeah, it looks pretty good now. You can see that this is definitely just touching this line. That is the slope of this curve at this point right here. That is literally the derivative, and now we have a value. It is 1/2. Okay? A little weird to think about, but I think the graph kind of helps illustrate it a little bit further. All right? Well, we can go the other way, actually, too. So this time, we're going to actually give the gradient, and we're going to say, okay, what point or points on this curve has a gradient of its tangent line being -9. Okay, so our curve that we're looking at is this function right here, and we're going to just try to see where the value of the gradient is -9. Well, basically, if we're trying to find where the gradient is -9, we need the gradient function, aka the derivative. We need to take the derivative of this guy. So we go ahead, we take the derivative of it. It's not a bad derivative to take, so it is 3x squared plus 12x. Review the power rule if you're not comfortable doing that yet. And we need to find points where dy dx is equal to -9. So I'm just going to plug this guy in right here, and then we're going to solve for x. And it's going to end up looking like a quadratic, okay? So I move the 9 over, I go ahead, I factor out a 3, and then I factor this inner trinomial right here. And I end up finding out that x is equal to -1 or -3. And that is where the y-coordinate will actually come into handy, because now that we have the x-coordinate where it occurs, we need to actually find those points on the curve where it has a gradient of -9. So we have to actually take those x values and plug them back into our original function to find those points. Okay? So we take this original function, and we're going to plug these guys in and just find out what y values we get back. So I do this with my -1, I plug it in, and I end up finding that -1, 10 on that original curve, that's where it has a gradient of -9. And likewise, I do it with x equals -3. I think you guys can do that. And y equals 32. So -3, 32 also has a gradient of -9. Those would be our answers. Those are our solutions to this problem. But once again, let's look and see what this curve is doing, and let's see if the gradient is indeed -9 at those points, right? So let's hide this guy, and let's show this guy right here, okay? So it's a cubic function, so it looks like this, okay? But apparently at point -1, 10, I guess I'll do it like this, -1, 10, and, oops, it's not going to detect it like that. I got a little ambitious right there. -3, 32. Those are the 2 points that have a slope of -9. And I'm going to go ahead, I'm going to plot a -9x line, a line that has a slope of -9, just so you could see this. And yeah, again, you know, it's a little off because, you know, the line's y-intercept's kind of off. But again, you see that the slope at these points, yeah, it looks like they're going down at a slope of -9 at those particular points, which is kind of interesting to see. All right, so now let's return to our original question and try to solve that problem now that we have our skills. Okay, so here's the thing. Sea level and Mount Everest, we need to find their distances in meters, which I already did for us. And it's really not that different, right? They look pretty similar. So it's just, you know, an extra like 9,000 meters from sea level is Mount Everest, okay? First things first, we need to find the derivative of Newton's law of gravity, okay? Now, I already did it right there, but I am going to show you how I came up with that guy. So this G, this M, those are not my inputs. Those are constants. And just like we deal with like, you know, like 4x squared or something like that, and we want to find the derivative of that guy, well, dy dx, we can kind of like, we haven't been doing this, but we've kind of been like we take this 2 and multiply the 8 and everything, but we're really like applying the power rule just to like this exponent, and we're kind of like moving the 4 off to the side and just trying to find the derivative of x squared. Okay, so you end up getting 2x, and obviously you have to multiply that by 4 to get the 8x. Okay, so these constants, we can kind of actually just move them to the side like this, and then we end up with r to the negative 2. And this is something we can definitely do the power rule of. So I'm just going to focus on this r to the negative 2. I'm going to take the negative 2, put it out in front, so we get for dfg over dr, the change in the force of gravity with respect to the distance, is equal to negative 2 times g m, and then it's going to be r to the negative 3, which is the same thing as moving this guy down here and making it r to the positive 3. So that's where I came up with my derivative. And these masses and gravitational constant, they're all constants. They are not going to change at all, which is why I was able to do that. So I go ahead and I plug these guys in to this equation right here. And then for my r, I'm going to take from sea level that distance from the center of the Earth, and then I'm going to do it again with this distance from Mount Everest, and we're just going to compare what the change in the force of gravity is with respect to distance for both of those. Really what we're trying to get at is, does it really matter, like are we experiencing a crazy gravitational change when it comes to sea level and Mount Everest? And that's kind of what we're trying to get at with this goose. That goose, okay? So I did it with R1, all right? I plugged all this crap into a calculator, plug it in exactly as I put it in your calculator as well with the TI-84, so parentheses and the whole 9 yards, okay? And I ended up getting negative 6.16 times 10 to the negative 4 newtons per meters, which is approximately this tiny, tiny small number, really small change. We'll talk about that result in a little bit. I went ahead and I did it with the second radius or distance. Top is the exact same copy. The only difference was, this distance right here. And I ended up getting something very, very similar, actually, almost identical. And so the units for this guy, if we think about it, the force of gravity is measured in newtons. Our radius or distance is measured in meters. So it's in newtons per meters. Think about that with like miles per hour when you're comparing your distance and time, right? As time moves forward and you're in a car, you're going farther and farther and farther. So that slope is in meters per second, which is a speed, which is a velocity, right? This isn't necessarily a velocity, but basically going back to the speed, every second you're traveling a certain amount of meters. That's your speed. So every meter we move at Mount Everest right here, down here, or at sea level right here, every meter we move, we only experience, and really this goose only experiences a negative 0.000616 force of gravity change in newtons. That's kind of small, very insignificant. And that's actually really good, because if you think about it, just because you hike the Wallapies, you're not going to experience crazy gravitational changes that throw you off. Really nice. I mean, the only thing you got to deal with, is people and high elevation. That's it. If you're a goose in this case, you don't have to worry about any gravitational changes. You just need to be worrying about being a goose. You know what I mean? And not freezing to death because you're a goose. And you're 200 kilograms, man. Maybe it's for the best. But I'm rambling now. This is Mr. Knight signing off. Exercise 5C is the homework that is associated with this lesson.